Hey there. Okay, so this week we've got a video about Fit and some updates to that particular tool, and we've got with you here Owen Alexander. So Owen, take it away.
Thanks, Carl. Fault injection testing is the process of testing a system by simulating particularly disruptive scenarios and seeing if the system can respond and recover and get back to the good state. So for mission critical industries, this means testing safety requirements derived through safety analysis such as FMEA and HAZOP. So the reason this is an important thing to do is that in certain conditions, problems can occur with a system that lead to serious failures that are difficult to test and difficult to repeatedly test. So, for example, there's a case at Toyota, which there were enormous losses due to software faults and controller trouble, which can be prevented with fault injection testing. So the reason this is such a difficult thing to do is that an artificial fault has to be created and injected during the execution of the program and see how the controller responds to that fault. This is hard to instrument, it's time consuming, and it may require code changes such as hard coding values, which is a risk in development. So this is where our tool Fit comes into play, our fault injection tester. So this tool is automated fault injection testing, and it is one of the first automated fault injection testing tools to be made. This helps with the process of fault injection testing by reducing the risk exposure, making the testing environment easier to set up, and automatically generating test cases to help create real world failure conditions. And I'll let Amol talk a little bit more about the advantages of our tool.
Thank you, Owen. So it helps with automated fault injection testing. So it's as easy as you have a test case for what fault you want within your setup that's injected into your system. That will be carried out, and then you observe what the system does given that scenario. As Owen mentioned, this reduces a lot of risk because if you want to do fault injection testing without such a simple setup, you have to create some way that the system will believe that some other part of the system is failed or is not working, or is getting extraneous values. So this could be changes to the code, and changes to the code that are not only for testing, but would have to remain in the code even when it's out in production. So, if you have some code that's only there for testing, but it's in production, it could execute when it's in production as well, and you definitely don't want that. So it uses minimum implements, instrumentation, and with that, you don't have to make changes to the code, but you can still do your testing. This saves a lot of time and money because, of course, if you want to inject those faults with making code changes, you have to ask your engineers to go to the places where you're going to be testing, put those segments of code in, and then run that through. So this saves a lot of time. It's quite significant. And another thing is, so if you're doing fault injection testing, the way that I mentioned, where you're trying to make the system believe that some other part of the system has failed and actually believe that, or making changes to the code, you have to make other instrumentation to see what the system does after that. You can either see it by maybe you're looking at logs, or if it's already an integrated system, you can see the setup of the system. Like if we're talking a car, maybe there's some warning lights or something like that needs to show up. But with our tool, you can actually see what's called the task graph. It's pretty commonly used in real-time systems, which shows at what time a given task, which is just some function or process that's running to do something, is running or not running. So this visual task graph, it's usually used just in, if we're talking hypothetically, this is going to run, this is going to run, this is going to run. But if it gives you that visual after you injected a fault, it makes understanding the system's behavior due to that fault a lot easier. And you can also see visual values of given variables in the code. So not only the task, but if you have, say, a variable for the speed, the case that Owen mentioned was unintended acceleration. So it was quite a bad scenario where the driver, couldn't brake at all. The system was not responding to the brake pedal. So if you have a speed variable, you can see that the speed would be indefinitely increasing. So all those things both save time on your analysis end, because you can clearly just see visuals of what's happening to the variables, what's happening to the task, to understand the system behavior. And then also for softwares that need to meet certain certifications, so relevant to automotive is ISO 26262, which requires fault injection testing. They can help you meet that with ease. So those are some of the main features. To summarize them, there's no additional hardware or software needed. Most of the components that FIT will use, you would already have if you're doing fault injection testing the manual way. So there's no additional implements that you need. So it doesn't cost a lot of money. You simply need the software and then the setup. And another notable feature is that it generates faults automatically. It looks at the system and things that would commonly go wrong. And so those will automatically generate, and then you can have additional faults on your own. And then, like I said, it makes the test scheduling graphs. It makes it easy to understand what's going on. Variable graphs, understand what's going on again. So you can see particular values. You can set even triggers that if this variable exceeds this amount, flag that in the software. So after you run a fault, if you see a flag, that's a failure, it could be. And then in addition to all that, you can export all that into a report in a couple of seconds. So that can be helpful for proof of results for your test that I conducted this test. These are the results, and this is what happened. You can look at all the data and things of that nature. So overall, holistically, I mean, it saves a lot of time in the setup, it saves a lot of time in the testing itself, it saves a lot of time in the analysis to understand system behavior, and that can even help the engineers design a better system, and saves a lot of time in your testing overall, because you can just export the values and the results are right there. They speak for themselves. So that's all for the main features of it.
It's fantastic. I really liked what you talked about there. Did Owen need to add anything else, or were you kind of done with that there?
No, that was it.
That was it. Okay, great. Thank you very much. I mean, I think that was fantastic. And I loved how you summarized it as well. So if anyone has any questions about FIT and about how it could fit into your particular software testing workflow, please get in touch with us, and we'll be more than happy to answer any questions you might have. Thank you.